A groundbreaking leap in optics could redefine how we explore the cosmos. Gravitational wave observatories are on the verge of a dramatic upgrade, thanks to a pioneering technological innovation spearheaded by physicist Jonathan Richardson from the University of California, Riverside. In a recent publication in the journal Optica, Richardson and his team introduced FROSTI, a full-scale prototype system capable of controlling laser wavefronts at extraordinarily high powers inside the Laser Interferometer Gravitational Wave Observatory, more commonly known as LIGO. LIGO is renowned for its ability to detect gravitational waves, tiny, almost imperceptible ripples in space-time generated by massive, accelerating cosmic objects such as colliding black holes. This observatory made history as the first to capture these elusive waves directly, offering powerful confirmation of Einstein's theory of relativity. With its two 4-kilometer-long laser interferometers located in Washington and Louisiana, LIGO can detect astonishingly subtle disturbances, providing scientists a novel window into the mysteries of black holes, the structure of the universe, and the behavior of matter under extreme conditions. At the heart of LIGO's precision are its mirrors, some of the most meticulously engineered components in modern science. Each mirror measures 34 centimeters across, 20 centimeters in thickness, and weighs roughly 40 kilograms. Detecting space-time distortions smaller than 1,000th the diameter of a proton demands that these mirrors remain almost perfectly still. Even the slightest vibration or environmental interference can obscure the delicate gravitational wave signals LIGO aims to capture. The key to our breakthrough lies in an innovative adaptive optics system that can precisely reshape LIGO's primary mirrors under laser powers exceeding 1 megawatt, over 1 billion times more powerful than a standard laser pointer and nearly 5 times the intensity LIGO currently employs, explained Richardson, who serves as an assistant professor of physics and astronomy. This technology opens a crucial path for the future of gravitational wave astronomy. It sets the stage for next-generation detectors like Cosmic Explorer, which will peer further into the universe than ever before. FROSTI, fine-tuned thermal control for LIGO's mirrors. FROSTI, which stands for Front Surface Type Irradiator, is an advanced wavefront control system designed to counteract distortions caused when intense laser beams heat LIGO's optical components. Unlike existing systems that can only provide relatively rough corrections, FROSTI employs a sophisticated thermal projection technique that allows for subtle, high-order adjustments to the mirror surfaces. This precision is vital for meeting the rigorous demands of future gravitational wave observatories. Despite its chilly name, FROSTI operates by gently warming the mirror surfaces in a highly controlled manner, restoring their ideal optical shapes. The system projects a carefully designed heat pattern onto the mirror using thermal radiation. This process smooths out optical imperfections without introducing additional noise that could mimic real gravitational wave signals. Why superior optics are essential for gravitational wave astronomy. The first detection of gravitational waves by LIGO in 2015 marked a revolutionary moment in astronomy, opening a completely new way to study the universe. However, to fully harness this capability, upcoming detectors must observe more distant events with higher precision. Achieving this requires pushing the boundaries of both laser power and quantum-level measurement accuracy, Richardson noted. The challenge is that higher laser power can disturb the delicate quantum states crucial for improving signal clarity. Our new system overcomes this problem by ensuring the optics remain undistorted even at megawatt power levels. By maintaining perfect mirror shapes at extreme powers, this technology could expand the observable gravitational wave universe by a factor of 10. This dramatic increase in reach may allow astronomers to detect millions of black hole and neutron star mergers throughout cosmic history, offering unprecedented insights into their behavior and evolution. Looking forward, LIGO A# and Cosmic Explorer. FROSTI is set to play a pivotal role in LIGO A#, a planned upgrade that will serve as a testing ground for the ambitious next-generation observatory, Cosmic Explorer. While the current prototype has demonstrated success on a 40 kg LIGO mirror, the underlying principles can be scaled up to the much larger 440 kg mirrors envisioned for Cosmic Explorer. This prototype is just the start, Richardson emphasized. We are already designing next-generation versions capable of correcting even more complex optical distortions. This work lays the foundation for the next 2 decades of gravitational wave exploration. Richardson conducted this research in collaboration with scientists from UC Riverside, MIT, and Caltech, with funding support from the National Science Foundation. But here's where it gets controversial. Could pushing LIGO to higher laser powers introduce unforeseen risks to measurement accuracy? Are we reaching the limits of what even the most advanced optics can handle? These are questions the scientific community is actively debating, and we'd love to hear your thoughts. Do you agree with the push toward megawatt-level laser precision, or is caution warranted? Join the discussion in the comments below.